So today we're going to talk a little bit about network diagnostics, and we're going to go through and demonstrate hooking up the picoscope to a network on a vehicle and observing what kind of waveforms we can access through the DLC. So we're under the dash on this 2014 Volt, and we're going to take a look down here. We have the DLC right in front of us, right up under the dash here. And if we look closely, we can see that a couple of these pins are populated, but this is not a fully populated DLC. This vehicle is actually unique in the fact that it has two DLCs. This one is the OBD compliance DLC. GM felt that they needed an additional DLC for some hybrid diagnostics. So there's an additional DLC actually over on the passenger side. But this particular DLC, we have pin 1 populated, pin 16 is populated, pin 4 and 5 is populated. Those 4 pins are typically almost always populated with some sort of pin. 4 and 5 are actually grounds. 4 and 5 is actually up here. 16 is power. And typically I try not to probe these. The reason I try not to probe these is you're going to have to front probe these, and if you do not use the correct size terminal, you're going to stretch those MetroPack terminals. These are also high wear connectors, so oftentimes on our lab vehicles they can get stretched out pretty easily. So this is something I don't try to probe very often. So instead of probing them directly, I use something like an OBD breakout box like this right here. And this OBD breakout box allows us to do the probing on banana plugs, and this end would go into the vehicle, and then this other end you can actually plug a scan tool in also. So you can do, it works as a pass-through for our scan tool. So we're going to hook this up, and we're going to use this during our probing for the picoscope. So go right under here, plug that in. And if we take a look, pin 16 is lit up. So we've got pin 16 right on the end there. It's lit up red. So we do have voltage there. And we've got pin 4 and 5, which is our chassis and signal ground, that are lit up. So now we're going to go ahead and start up our picoscope. So we're going to go right over here. I've already got our picoscope hooked to the laptop. We're going to bring the software up. It looks like it didn't find our device. So we've got our picoscope fixed up, and we've got it sitting here. And we're going to go ahead and hook our terminals up for that, and we're going to see what kind of waveform we can get. So I'm going to preset this. We're going to set this to about 5 volts. And then we're also going to turn channel B on and set that to 5 volts. We're going to stick with 5 milliseconds of division for now. We might have to change that once we get a waveform up here. Now that we've got both probes hooked to the picoscope, we're going to go ahead and tie our grounds together. So we're going to put our two ground plugs from our 2 channels together. We've got two independent channels here, so that we can measure both sides of one of the networks. So the network we're going to be scoping today is a CAN bus network. CAN bus network is a 2-wire network, so it's 2 wires. One is pulled high, one is pulled low. So we need 2 channels with a scope to scope that. So we're going to go over to the vehicle now and take a look at that. So we're going to go over here to the vehicle and take a look at our breakup box. Real simple. CAN bus networks, if we were to look at our DLC again, so under here, our CAN bus network is 6 and 14. And conveniently they're right above and below each other. So remember, these 2 on top, I'm blocking the shadow here, but these 2 on top, 4 and 5, those 2 are our grounds, so 6 must be that one. And then 14 is right below 6. So a lot of the 2-wire networks, the DLC is set up in such a way that the 2-wire networks are right above and below each other. So those are the 2 wires we're going to be probing. So plug that back. And then we're going to take our probes, and channel 1 we're going to go into CAN low right there, and channel 2 we're going to go into CAN high. So let's go back to the picoscope screen, and we're going to see what we get. So now that I've started recording, if you take a look at what I've got on the picoscope, we've got a series of bars going back and forth, and actually down just now the vehicle went to sleep. So the CAN bus is idle. Another way you can tell this, as I'll show you in a minute, but we can actually see the CAN low and CAN high channels flickering on the breakout box. That would just tell us there's a message there. But on the picoscope, these are going to show up as square wave waveforms. So I'm going to take the key fob here and I'm going to hit the unlock button, and you're going to see now suddenly the network's come alive. So these are all CAN bus messages. I'm going to drag low and high out separate from each other. But these are CAN bus messages, and if we set up a trigger, we'll just set one on channel A. We'll set it down here, and we've got to set it up for falling rate. Hey, channel B is a little better candidate for this. Drag this up. So these are all CAN bus messages that are going on in the vehicle. Typically, most computer communication networks are pretty dense on their communication, and most of the time you're going to see this sort of activity with CAN bus. So a lot of these messages, if we zoom out or zoom in a little bit here, a lot of these messages are actually digital switching. So this is one or more modules digitally pulling these CAN low and CAN high wires to a higher voltage or a lower voltage. If we zoom in on this even more, we can see that all the switching is pretty clean, pretty static. All the bars are very vertical, and what this represents is, if we zoom out here, all of these areas, so like say for instance this guy right here, this would represent a packet of information on the CAN bus. So these packets are like messages, and these packets will transmit a certain specified message to a certain module. So within that packet we have things like where the module that sent it is, whether or not, or what address the other module that needs that message is. So it's going to essentially put it in an envelope and address that message with everything that that module needs to say within that packet. So that packet is essentially your letter that's being sent from one module to another. Understand that this is happening very, very fast. So we're down in the millisecond scale right here. So if I drag some of these rulers out, let's actually do this packet right down at the end because it's going to be easy. We'll drag this ruler right out to the end of that message, and we'll drag another ruler just to the beginning. And we notice this entire message packet takes about 209 picoseconds. So that's millions of a second. Okay, so these messages are extremely fast. So one of the reasons we use communication networks on vehicles is for fuel economy and cost of features. So a lot of manufacturers have recognized that the cost argument is something that we really want to pay attention to. So that fuel economy and cost are tied hand in hand, because the fuel economy and the cost are brought down with computer networks, because we can essentially add features and things like that. We can connect interconnected networks and modules in such a way that we do not have to wire them directly to send signals from one end of the vehicle to the other. So a classic example of this is, let's say in our engine performance scenario, we have a traction control module that is having a difficult time controlling wheel spin. That electronic brake control module, which is already maybe modulating brakes and things like that, can actually send a torque reduction request to the powertrain control module to say, hey, I need a little less engine torque. We can do things like upshift the transmission or retard ignition timing. We can even get as far as cutting fuel injectors out as well to reduce some of that engine torque. So the engine runs a little bit worse, but in that scenario, we might be preventing an accident or something like that in that traction control scenario. So we know computers communicate digitally, so we're talking about communicating digitally in ones and zeros. These are ons or offs, that's it. So as we saw on the picoscope, we can either pull voltage high or we can pull voltage low, that's it. Multiple modules can communicate on the same wire. So on CAN bus, when we were looking at the picoscope, we were likely looking at 5 to 7 modules that while the vehicle was off and the key fob was activated, we were looking at about 5 to 7 modules that were sending messages back and forth. And that's called intermodal communication. So we're going to take a look here. The need for it, we can do data requests, we can do scan tool diagnostics with these networks. In engine performance, we have ABS, traction control, vehicle speed control, electronic throttle control even in some case, even things like rolling your window up. Everything's a request now, not a demand. So we can expand our portability, we can lessen our cost, and we can use more modules and more areas for more tasks. There are 2 types of network wiring. Most of the networks nowadays have gone to a star network configuration. That is not always true. There are still some examples of serial networks, but essentially these are how these networks are wired. The star design makes diagnostics pretty easily because we could have one module drop off the bus. We really only have to worry about that link between that module and wherever it starts communicating with the rest of the modules. So a lot of times those branches of that bus can make diagnostics pretty easy. Here's an example of a serial network. This is a GM. So again, we've got our body control module right down here up at the top. I want you to pay attention to this. This is our data link connector. So this is our DLC under our dash. Notice 4 and 5 are populated. 16 is populated with a 20 amp fuse, so that's our power. And then pin 2 is the only other pin that's actually populated on this connector. So pin 2 comes down here. We see serial data, class 2. That's GM's name for the 1996 OBD standard that said all vehicles have to communicate with the powertrain control module and output emissions information on that wire. So that wire is the same as this guy here. And that purple wire travels all through the vehicle, looks like at the instrument panel cluster here, and then proceeds on. And again, this is a serial network, so proceeds on through that module to the inflatable restraint sensing and diagnostic module, also known as airbag, and then goes down here to our EBCM, and then proceeds across here to our powertrain control module. I am doing this with a mouse pad, so pardon my terrible drawing. And then we go back up here to our body control module. So the interesting thing about this style of network is it is redundant. So if we lose a link, so let's say we had a failure somewhere in this link, let's put our failure right here. If this wire was open, we would actually be able to back communicate the other direction. So any of these modules on this network can pull this network high or low, meaning that as long as we have one link, all of these modules communicate with it. So it's a serial network, but it does not go in one direction. Communication can go either direction. So if the body control module wants to send a message to the PCM, it can do that. It can do that through that link there. But if that wire is not good, it cannot go this direction. The message will still get there, it just gets there in a different end. So that's one of the nice things about this particular network architecture. Here's our YTech diagnostic application. If you notice, this looks an awful lot like a wiring diagram, and one of the smart things that Chrysler did when they developed this scan tool software is they decided that the network architecture would be on the home screen as soon as you connect to the vehicle. So when you connect to the vehicle, this is what you see. You can see this is mostly a star network configuration. We've got 2 main branches of this network with all of our modules that are on the network. So this is a 2008 RT 3.8 liter. This is a Charger from 2008. Notice how many computer modules are on that network. here's our ones and zeros, typical there, nothing new there. And then we'll go over binary and things like that in class. So we know most of emissions spec that the DLC is down under the dash, so we're used to that by now. That's not really going to change anytime soon, but there are specifications that are almost constantly changing for which pins are which. So right now the popular pins are pin 2. So pin 2 for OBD2 and 11 for OBD2, pin 4 and pin 5, which are our grounds, pin 16 for power, and then pin 16, or 6 and 14 for our CAN bus. So CAN bus is a new standard. It was adopted in 2006, and CAN bus is something that's more recent but has become kind of the standard across vehicle manufacturers. As far as diagnostics, the biggest and easiest way to diagnose network systems is remembering a 3-step test. You look at power, you look at ground, and you look at communication. So the same test that we did at the DLC on the picoscope, we can do at individual modules. So if you have a module that we can't communicate with via scan tool, we can go directly to that module and check for power, check for ground, and then also check for that communication signal. So we can back probe CAN wires, we can back probe some other network wires, and take a look at the scope and actually see that network switching activity and determine whether or not that signal is getting to that module. Those are all valid tests. You can also sometimes run into modules that communicate too much, so we'll talk about those during class as well.